Good evening. My name is Lwazilwe Nkosindlovu, and I'll be presenting to you the electromagnetic spectrum today. Well, if you can just dive straight into it. Right. So we are going to look at the properties and principles of electromagnetic waves. Then we'll move on to properties of microwaves and infrared. From there, we'll just look at the uses and hazards of X-rays in medical applications. Then we'll move on to a comparison of visible and UV light and also the applications. Then finally, we'll look at the biohazards of ultraviolet and infrared radiation and their main effects. Right, if we can look at a quick definition of the magnetic spectrum. Right, so I've got it here as electromagnetic waves are propagated by concurrent periodic variations of electric and magnetic strength, and that comprises of radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Right, so the distance between the peak of either oscillation is called a wavelength, and the frequency is the number of peaks at a time. Right. Let's look at the properties now. Electromagnetic waves are transverse in nature, and they propagate by varying electric fields and magnetic fields such that the fields are at right angles to each other and the direction of propagation of the wave. Right, they travel in a vacuum at a constant velocity of at the speed of light, which is 300 million miles per second. And they do not require any material medium for propagation, therefore are non-mechanical waves. I'm just going to quickly demonstrate that in a diagram, which will be our figure 1 for today. And right, so on this diagram, we've got two waves, okay, the red being the magnetic field and then the blue being the electric field. Okay, so these two fields are propagating, or basically their movement is shown by the arrows there, which is the propagation direction, right? Then they meet right in the middle there, which is basically the equilibrium or the medium point, the middle point, right? So where they meet right there in the middle point, it's always a right angle. They form a right angle, which is 90 degrees. They're always 90 degrees to each other. Right, so we've got these loops, or we can call them crests, right? The distance between each two crests, the two crests there is called the wavelength, right? And then we've got the distance between the midpoint to the crest, which is referred to as the amplitude. Right. So by oscillation, we're talking about the waves turning towards that propagation direction. Right. I hope that's clear for everyone to understand. Right. If we can move forward from that, back to our properties. So this electromagnetic waves can be reflected, refracted, and diffracted, which basically means that they can change direction, right? They can be thrown back without being absorbed, and they can go around obstacles, right? And well, they follow the general wave equation, which is speed equals to frequency multiplied by wavelength. Okay, so let's move on from that. Let's look at the properties of microwaves. So microwaves are the band of electromagnetic spectrum that is between infrared and radio waves. Okay, so they just lie right in the middle, right there between the infrared and the radio waves. Okay, so they're unidirectional and communicate along a line of sight route. Okay, I'll illustrate that in a diagram as well. But before I do that, let's just look at more properties there. Okay, so they consist of changing magnetic fields and electric fields as well. And just to mention a few there. So let's look at figure 3. Right, so we spoke about them communicating through a line of route. So we've got our stations here on this diagram. Okay, this is basically a relay station, right? So in this relay station, we've got the wave being transmitted from that station, which it will be the main station, to there and to there, or vice versa, right? But in this case, we'll get like based on the thing, on the properties that I've just explained, you'll have your wave being transmitted from this, say this is your base station here, this is your receiving station, right? It will be transmitted from your base station going all the way to your receiving station through this line of sight route, which is here about 30 miles as it says, right? Then since this is a relay, this is a relay diagram, so that this wave will go all the way from there to there and be relayed to all the way to the end station there. Right, so it's always still on the line of sight route. Okay, and it's unidirectional, which means it's only going one direction at a time. Right, then we've got microwave ovens as well, the domestic microwave ovens we all use at home. Microwave ovens oscillate water molecules, causing localized superheating from inside the food. Okay, again, we've got a diagram there of this will be our illustration of a domestic microwave, right? So in this diagram, we've got your food item right in the middle there. Then we've got your microwaves shooting directly towards the food. But now what it does is it will heat up the water molecules in the food there, all targeted right in the middle. Then you have like your localized heating, which is basically starts from inside the food out. So it will heat the food from the inside out. Okay, now let's look at the properties of infrared. Okay, so the infrared, it occupies the band of spectrum between 700 Newton meters to 1 micrometer wavelength. Infrared radiation is emitted from objects that give off heat. Okay, so any object that gives off heat will emit infrared, be it a building, be it living organisms, be it mammals, people, right? They all give off heat, so thereby that translates to infrared. So they've got a longer wavelength than a visible light, and they can disclose objects in the planet that can be seen in visible light using optical telescopes. Okay, and they can pass through dense areas of gas and dust in spaces with less scattering and absorption. Okay, so if we can look at a diagram again, figure 4, okay, which should give us an illustration of what infrared can do. So this is a picture that was taken by an infrared camera. So basically in this picture, you've got all these red shades, right? The red shades, they indicate heat, which translates to infrared waves. Okay. So you've got a car there it's emitting a bit of heat. There's red shade on it. You've got people there with red shades on them. They've got a building with red shades on the road there. So all that indicates heat, which then translates to infrared waves, right? And again, we did say infrared can disclose objects in the planet that can be seen and can pass through dense areas of gas and dust. Let's take an example of military night vision goggles, right? Um, they pick up heat, right? Whenever the military guys use them, those goggles are designed to pick up heat, which then translates to infrared. So they are actually infrared goggles, right? So the minute they pick up that heat translates to infrared, and then they can easily see what's in front of them using those infrared waves. Uh, Right, moving on to the uses of X-rays in medical applications. Okay, so medical imaging to examine anything from broken bones, broken limbs, some type of tumors, abnormal masses, then some signs of pneumonia in the lungs. It can also be used to detect and investigate foreign objects in the body. Um, Dentists use it to check development of teeth in children. Also in adults, it can be used to check on any uh, uh, problems with the teeth. All right. Then the hazards of X-rays. We've got X-ray radiation can cause damage to molecular structure once absorbed within the body. Okay, so X-rays are linked to cancer, right? So in hospitals, basically, there's a certain amount of radiation that a person has to be subjected to. Otherwise, too much of it will be toxic to your body. So then it can cause loss of white blood cells and inability to fight infections. That means that um, it lowers your immune system, basically. It destroys your immune system. Then high exposure to radiation can level high exposure to radiation level has effects such as hair loss, vomiting, fainting, bleeding, radiation burns, skin redness, and death. So take for example someone who goes for chemotherapy. Okay, we've seen them lose hair and vomiting and whatnot. So that's a result of exposure to high radiation. Okay, so we've got here a comparison of the properties of visible and UV light. Okay, I'll just go through a few for the sake of time. So I've got here visible light. It is one small band of electromagnetic radiation that is visible to the human eye. Okay. White light is composed of different colors of the rainbow. So said Isaac Newton in the 1600s. And on UV light, you can simply UV strengths are shorter than the visible light wavelength. UV rays could be blocked by thick clouds. Okay, so we've seen when the sun is out, then suddenly it gets cloudy. It just changes, it becomes dark. That means that the UV lighting has been blocked by the clouds. UV lights used to disinfect through hospitals and lab, and it's invisible to the human eye, unlike the visible light. Okay, I think we can move on from that. Let's look at the application of visible and UV light. Okay, so UV radiation is used in industrial, medical, and dental processes to kill bacteria, create fluorescent effects. Okay, so take for instance, sometimes there's usually dirt that you can't easily see by naked eye. So you have to use a fluorescent light to to be able to determine if there's dirt traces, there's fingerprints, there's also all those sorts of things, which explains that part there. Then it's used to curing inks and resins, phototherapy, sun tanning. Sun tanning can either be natural or artificial. Okay, you can get sun tanning directly from the sun by simply lying outside when it's sunny, or you can use machines, man-made machines, sun tanning machines, and that's it. So UV light can be used for photography, illumination, fiber optic communications, which is basically your phones and whatnot. Right, the biohazards. Right, infrared radiation will hurt and burn. Right, we feel heat emitted from hot objects. However, the greater danger will be direct contact with the hot object. Say you heat up a metal, it turns red. Then if you touch the red part, that's where the danger is. That's basically what it means there. And intense focused infrared light can cause damage to parts of the eye. UV light can break chemical bonds in molecules and cause chemical reactions to occur. Right. Too much exposure to UV light can penetrate into human cells, causing chemical reactions to DNA, resulting in mutating and cancerous cells developing. Okay, so UV light can basically change your DNA, that's what it means, and causing your cells to be abnormal, right? Once the cells are abnormal, that basically translates to them being cancerous, and that will be very harmful to any human being. All right, now to conclude, the electromagnetic spectrum is broken down into 7 areas, namely radio waves, microwaves, infrared, visible, UV light, X-ray, and gamma rays. We've touched on all of those, and we use the electromagnetic spectrum in our daily lives, be it in medical practices, household uses. Some examples use visible light to see, radio waves to communicate, or watch TV, and microwave to heat up food. So without the electromagnetic spectrum, there would simply be no life. That brings us to the end of my presentation. Thank you.